Hi, I'm Nicholas Dwork, and today we're going to discuss the derivative. First, we need a metric of difference. A simple metric is just x minus x reference, and very related to that is the absolute difference, which is the magnitude of x minus x reference. So if x is 10 and x reference is 11, then the absolute difference would be 1. The issue with absolute difference as our metric is that 1 doesn't tell the whole story. If I tell you the absolute difference is 1 and x reference is 1,000,000, that seems pretty close. But if I tell you that the absolute difference is 1 and x reference is 1, that seems much farther away. So instead we use relative difference, where we take the absolute difference and divide by the magnitude of x reference. When the reference is large, you need a much larger difference to get the same relative difference. And this is often expressed as a percentage. Now let's talk about mountains. Any hiker will tell you it's a lot harder to traverse a mile horizontally when the mountain is steeper than when it's shallow. And so we want some number that represents how steep the mountain is. How hard is it going to be to climb that mountain? And the metric that we come up with is the slope. We look at how tall the mountain is. We look at how far we have to travel horizontally in order to move that height. And we take the ratio of those two values. So the slope is delta y over delta x, and it's commonly described as rise over run. We can impose these lines on a coordinate system, and now we can measure delta y and delta x, and m becomes a number. We could connect the endpoints of these line segments, and we get a new line. And now the function of that line involves the slope, so f of x is equal to mx plus b. Here, m is the slope, and b is what's called the y-intercept. It's where the line intersects the y-axis. Here's an example. F of x is equal to x plus 3. The slope is 1. The y-intercept is 3. Here's f of x is equal to negative 2. This has a slope of 0. And here's f of x is equal to negative 1/2 x plus 1. Here the slope is negative. Suppose we have samples of a function that maps the real numbers to the real numbers. What does it mean to have samples? Well, that means we know a set of ordered pairs where xi is in the domain and f of xi is in the range. So we have examples where we know some of the inputs and outputs of our function, and we want to approximate f at some new point y. Linear interpolation is a very common and reasonable way to do that, and what you do is connect nearby points with a straight line. So what does that look like? Here are some samples on a graph. Maybe we want to approximate f at this new point y. We'll draw a line between the nearest points x2 and x3. We see where y lies on that line, and that becomes the approximation of our function. Here's an example where we have 2 points, the function evaluated at x1 and x2. We've connected them with a line, and we want a function of that line. How do we find that function? We calculate the slope by computing the rise and dividing it by the run. The rise is f of x2 minus f of x1, and the run is x2 minus x1. That gives us the slope. Once you have the slope, the equation of the line is f hat of y is equal to f of x1 plus m times y minus x1. So this is a slightly different format than we had before. You can, of course, rearrange this into the slope-intercept format, but this is a very simple form that we'll use a lot. Suppose we have a function f that is continuous at x0, and we want to approximate that function as a straight line when we are near x0. How would we do that? Well, we need to find m and b so that f of x is approximately equal to mx plus b when x is close to x0. Here's an example. We have our element of the domain x0. We evaluate the function to get f of x0. Then what do we do? Well, we can look at a second point to the right of x0, x0 plus delta x, and we can evaluate the function there to get f of x0 plus delta x. Now we have 2 points. We could use the equation of the line of the form for 2 points that I showed you previously. That gives us our expression. So the slope is just the change in f, which is f of x0 plus delta x minus f of x0, and the change in the domain is delta x. And then that gives us this approximation for the function f. That is a decent approximation, but the function might go wild between x0 and x0 plus delta x. So how might we get a better approximation? We can reduce delta x. That gives us a different line. We can reduce it even more. In fact, we can find the slope in the limit that delta x goes to 0. And this gives us the so-called tangent line. We give this limit as x naught goes to 0 of f of x naught plus delta x minus f of x naught all over delta x, a particular symbol, it's f prime of x naught, and we give it a name, it's the derivative. F prime of x naught is the derivative of f at x naught. When we have the derivative, we get this approximation for our function at x naught. F of x naught plus delta x is approximately equal to f of x naught plus f prime of x naught times delta x. This is a supremely important equation. This is the fundamental equation of applied mathematics. I'll say it again. F of x plus delta x is approximately equal to f of x plus f prime of x delta x. All we're doing under the hood is approximating a function locally as a straight line. We do this because curvy things are difficult, but straight lines are easy. And the whole trick is to approximate curves with a straight line and then just work locally, work in the nearby area. As long as we don't move too far, everything will be okay. Some definitions. A function is differentiable at x means the following limit exists at x. And a function is differentiable means that it is differentiable at every point in its domain. Note that if f, which maps the real numbers to the real numbers, is differentiable, then f prime itself is a function that maps the real numbers to the real numbers. If the derivative is differentiable, then we can compute its derivative as well, and this is called the second derivative of f. It's denoted f double prime. The third derivative is denoted f triple prime. And after that, we just denote it f to the kth. So the fourth derivative would be f to the parentheses 4. Some notation. C is the set of continuous functions. C1 is the set of continuously differentiable functions. That means the first derivative exists and it is continuous. Ck is the set of functions that are k times continuously differentiable. And a function is smooth means the function is in C infinity. It is differentiable an infinite number of times. Changing topics slightly, here's a new definition. The epigraph of a function f, which maps its domain D to its range R, is the region above and including the function. So if this is our function, the epigraph is everything above the function and the function itself. Note that for a function that maps the real numbers to the real numbers, the epigraph of that function is a subset of R2. Here's a particular set that's going to be very important for us, the augmented reals. It's the real numbers union with the value infinity. In particular, we're going to think about functions that use this set as their range. A function whose range is the augmented reals is bounded below. So a function might diverge to infinity. It might even equal infinity in some locations, but it doesn't diverge to negative infinity, and it certainly doesn't equal negative infinity anywhere. A function f that maps its domain to the augmented reals is convex, means that all line segments connecting points on the graph lie above f. So let's look at two examples. Here's a graph. I've chosen 2 points on the graph of a function, and I've connected them with a dashed line. And sure enough, that line lies above the function. If you choose any 2 points on the graph of this function, that dashed line will always lie above the graph, therefore this function is convex. Here's a case where I've chosen 2 points on the graph of the function. The graph dips above the line segment connecting those 2 points, therefore this function is not convex. A function f that maps its domain to the augmented reals is convex, means that for all points x and y, if we take any value on the line segment connecting x and y, so 1 minus gamma times x plus gamma times y, and input that into our function, that value will be less than or equal to 1 minus gamma times f of x plus gamma times f of y. This says in math what I said in words at the top of this slide. Equivalently, a function is convex when its epigraph is convex. Here's a particular function. It's a very important function for our purposes, and it takes the value of infinity. It's the indicator function for a set. So I sub c of x is equal to 0 when x is in the set C, and otherwise it equals infinity. If C is a convex set, then the indicator function of C is a convex function. A function can also be concave. It means that all line segments connecting points on the graph lie below the function. If a function f maps the real numbers to the real numbers and is twice differentiable, then the second derivative is positive over intervals where the function is convex, and negative over intervals where the function is concave. So here's an example. Wherever the function is curved downward, the second derivative is negative, and wherever the function is curved upward, the second derivative is positive. A point where the second derivative changes from positive to negative is called an inflection point, also when it changes from negative to positive. A point x is a local minimum of function f that maps the real numbers to the real numbers means there exists an interval I from a to b, an open interval I, such that x is in I and f of x is less than or equal to f of y for all y in the interval I. Similarly, a point x is a local maximum of the function, means there exists an interval I such that x is in I and f of x is greater than or equal to f of y for all y in I. A point is a global minimum, means that f of x is less than or equal to f of y for all y in the domain of the real numbers. And it's a global maximum, means that f of x is greater than or equal to f of y for all other points y. So here's an example. Here are two local minima. Here's a local maximum. And this local minima on the right is also a global minimum. This function does not have a global maximum. Suppose we have an expression for the derivative of f, which maps the real numbers to the real numbers. The set of local extrema is the preimage of 0. So we can find all the local minima and maxima simply by figuring out where the derivative is equal to 0. That's because the slope at those points is 0. So here's an example. Hopefully you could see from this graph that the slope of the tangent line of -1 and at 1 would be 0. F of x is equal to x cubed minus 3x here. Its derivative is 3x squared minus 3. We set that equal to 0, and that means that x minus 1 times x plus 1 is equal to 0. So the local extrema exist at -1 and 1. If the second derivative exists, we can see if each point is a local min or max by observing the sign of the second derivative. For a function f that maps closed interval ab to the real numbers, there exists x and y in ab such that f of x is less than or equal to f of z for all z in ab, and f of y is greater than or equal to f of z for all z in ab. So what does all this mean? In words, a function attains its maximum and minimum over any closed interval. So let's say we have f that maps interval ab to the real numbers where f is differentiable on ab. How do we find the minimum and maximum points? Let's assume we have an expression for its derivative. First, you have to find all the points where the derivative is equal to 0. Those points that lie in the interval ab are local extrema of this function. However, it's not enough just to find those points, and an example is shown here on the right. The minimum of this function will be at a point where the derivative is equal to 0, but the maximum is not. The maximum is going to be at an endpoint a. So you also have to evaluate f at the endpoints a and b. You look at the value of those evaluations. The points where the function is the highest is the maximum, and the point where the function is the lowest is the minimum. Suppose that we are unable to solve for those points where the derivative equals 0. What can we do? What if we can't find the roots of the derivative? But we can evaluate the derivative wherever we want. So we have a function of the derivative, but if we set it equal to 0, we can't find its roots. What do? How can we find a local minimum? To figure this out, we're going to look at a geometric interpretation of the derivative, shown here. The derivative is an arrow that points in the up direction. So we see in the middle, the slope is 0, and so the arrow has no size. Its size is 0. As we move to the right, the slope increases, and so the arrow becomes larger. Similarly, if we move to the left, the arrow points left because left is the up direction, and it increases as we move further to the left. So if we want to find a minimum, and we know the derivative points up, we could just move in the opposite direction to the derivative. Here's an example. I'm going to evaluate a function, which I'm not going to draw immediately. Here's its evaluation. We could evaluate its derivative as well. The derivative points to the left, and it's pretty large. So that tells us the function is going up pretty quickly, moving left from this point. So let's move to the right some and evaluate the function again. We can evaluate the derivative here. We see that it's still pointing to the left, so we move to the right. It's not quite as big, so we don't move quite as far. We do this again, and again, and again. Now I'm going to draw the function, and you see we've gotten pretty close to the minimum. This is an algorithm called derivative descent, and here's what it looks like in code. The inputs are going to be our initial point x naught, some tolerance epsilon greater than 0, and alpha greater than 0. Alpha is called the step size. So we set x equal to our initial guess. We evaluate the derivative at x and store it as fpx. And then whenever the magnitude of the derivative is larger than epsilon, we're going to continue our iterations. The iteration is just what I showed you a moment ago. You take your current point and you subtract alpha times the derivative. That becomes our new point. And then we evaluate the derivative at our new point. That's the complete iteration for derivative descent. Derivative descent is guaranteed to converge to a minimum if alpha is small enough. So here's an example where alpha is small enough. It will eventually converge to a minimum, but it's going to take a long time. It might not converge to a minimum in your lifetime, for example. Here's a case where alpha is more effective and we'll be converging to a minimum pretty quickly, or we'll get close to the minimum pretty quickly. Here's an example where alpha is too large, and you see we're getting further and further away from the minimum with each iteration. If your implementation of derivative descent is failing, it may be that alpha is too large, too small, or there's a bug in your code. For example, you could have a bug in your implementation of the derivative. There are ways to automatically set alpha, and these are called line search. A simple approach is to reduce the step size until the function value has decreased. So let's see what that looks like. We're going to start here. Our alpha is way too large, so we end up way over there. And we see that the value of our function has increased. It's gone up. So we reduce alpha, and we try again. We're still going up. We reduce alpha. We try again. We've gone down. Now we can accept it. And we retain that new point. Here's what it looks like in code. You accept a parameter beta between 0 and 1, while true. So we're going to break out of this loop. X prime, our new point, is equal to x minus alpha times fpx. This is just our derivative descent from before. And x prime is our candidate new point. If f of x prime is less than f of x, then we break out of this loop. We accept that value of alpha. Otherwise, we set alpha equal to beta alpha, which reduces its size. Now this will work, but alpha will continuously get smaller. It may be the case that a larger alpha would be beneficial. So we set x equal to our candidate point once we broke out of this line search loop. And then we can grow alpha if we want to. We set alpha equal to alpha divided by beta. This last step is optional. There's another line search that's very popular called our Miho line search, and it's for functions that are continuously differentiable. It accepts a parameter gamma between 0 and 1. Let's see how it works. So this is our function. This is the point where we're currently at. We're going to think of this function now as a function of delta x. What value of alpha will give us the appropriate delta x to continue the minimization? We look at the tangent function of this line. Now remember, this is this supremely important formula, f of x plus f prime of x delta x. And we see that for a convex function, certainly, this tangent line lies below the graph. Then what we do is we multiply f prime by gamma, and that gives us a different line. And we see that this wedge identifies a region where it would be appropriate for us to continue our derivative descent. And so that's what we do. We figure out the delta x where the function f of x plus delta x is less than this upper line, f of x plus gamma f prime of x delta x. So we choose alpha small enough so that f of x plus delta x is less than or equal to f of x plus gamma times f prime of x delta x. With derivative descent, delta x is equal to negative alpha times f prime of x. And so this becomes our condition for our Miho line search. Derivative descent is a way to find a local minimum. What if instead we want to search for a root? That is, we want to find a place where our function is equal to 0. And we're going to assume again that the function is differentiable and we can evaluate its derivative at any point in its domain. Let's talk about Newton's method. What you do is approximate your function as a line. So we're going to start at this point, we approximate our function as a line, and we see where that line intersects the origin. That is, we find the root of that line. We then evaluate our function at that root of that line, and we approximate our function again as a line at that point. We see where the root of that line is. We evaluate our function again, and we go on like this. This is Newton's method. So in words, we iterate over the following. We approximate the function as a straight line. We see where the straight line has its root, and then we evaluate the function at that root. Let's see the equation of the Newton's method update. Let x sub n be your current guess. We're going to use the straight line approximation of our function. F of x is approximately equal to f of x of n plus f prime of x of n times x minus xn. And we want to see where this line has a root, so we set f of x equal to 0, plugging 0 in and solving for x sub n plus 1, we get this expression. This is the update for Newton's method. Now let's talk about stopping criteria for Newton's method. And by stopping criteria, I mean, when do we stop the iterations? One answer is just to run for a fixed number of iterations. And this has some good properties. The first is that we know how long it's going to take approximately because it does the same number of computations each time it runs. And the second is we know it's going to end eventually, so we won't get stuck in an infinite loop. The problem with this approach is that we don't know we got close to an answer. We just know it ran for a certain number of times. An alternative is to look at the magnitude of f of x. And if that's less than or equal to a tolerance epsilon, then stop. We know that f is small, so we're close to a root. Another option is to look not in the difference of the function value, but in the difference in the iterates. How far is Newton moving our estimate each time? And if that distance is small, if the magnitude of x sub n plus 1 minus x sub n is less than epsilon times the quantity, 1 plus the magnitude x sub n, then we stop. Now, where did this expression come from? Well, if x sub n is small, then that expression becomes just the magnitude of x sub n plus 1 minus x sub n is less than epsilon. So that's a way of saying if we've moved less than epsilon, then let's stop. If x sub n is large, then 1 plus the magnitude of x sub n is approximately equal to the magnitude of x sub n. And then the stopping criteria becomes this expression here, the magnitude of x sub n plus 1 minus x sub n all over the magnitude of x sub n plus 1 is less than epsilon. And this, you might remember, is relative difference. So we're saying if the relative change in our iterate is small, then stop. Those are three options for stopping criteria. Newton's method will converge to a root when x naught starts close enough and the function is smooth enough, but it's not guaranteed to always find a root. Here's one example where it doesn't. Here's f of x is equal to x to the 1/3. And the key here is that at 0, this function is strictly not differentiable. Its derivative approaches infinity as x approaches 0 from either the left or right side. Okay, so let's start here. We approximate our function as a line and we find a root and we evaluate our function again. We're slightly farther away. That's not good. We do it again and again. And each time we perform a Newton iterate, we get farther and farther away from the root. This is an example where capping the maximum number of iterations prevents an infinite loop. When you return in that situation, you can't say you're close to a root. You just say you've reached the maximum number of iterations. Here is Newton's method in code. It accepts inputs x naught, our initial guess, epsilon greater than 0, and max iter greater than 0. We set x equal to our initial guess. We set fx equal to this arbitrary value of epsilon plus 1, and you'll see why in just a second. And then we start our loop. So our loop continues whenever the magnitude of fx is greater than epsilon and iter is less than max iter. Iter is a value that's going to count the number of iterations conducted. So you see the first line within the while loop is just to set iter equal to iter plus 1. That is, we increment iter. So once iter gets to max iter, we break out regardless of what the value of our function is. And now you see why we set fx equal to epsilon plus 1. That way, at least initially, fx is greater than epsilon. So we enter our loop. In each iteration, we evaluate the function and its derivative at x, and then we do a Newton update. One application of Newton's method is to find a local extremum. Well, how do you do that? Recall that if you want a local extremum, then you seek a root of the derivative. And so this is the Newton's update when you're finding a local extremum. It's x sub n minus the ratio of the first derivative to the second derivative. This requires that the function be twice differentiable. Note, this only tells us where the derivative is 0. We still need to check if the point we found is a local minimum or a maximum. You could do that by looking at the sign of the second derivative. An alternative to Newton's method is bracketed Newton's method, and it assumes you have an additional input, a closed interval a,b, where you know the root is in that interval. So what's the approach here? You take a Newton step. If it lies outside the current interval, then you take a bisection step instead. Why do you do this? When Newton's method is working, its steps get smaller and smaller as it gets closer and closer to the root. So if you end up outside the interval, if you're taking gigantic steps, that indicates that something's wrong, but you could still make progress by taking a bisection step and eliminating half of your remaining interval. That does it for this lecture. Thank you for your attention.